Yeah. So welcome to today's online seminar. So I will give a presentation regarding graph representation learning. I already gave a very, very quick intro about this when we were in Thessaloniki, but this will be a more expanded view on the topic. So why do we need graph representation learning? Well, nowadays we use a lot of machine learning to solve many different kinds of problems, and it's becoming pervasive in all modern research in computer science because of its power, its ability to identify patterns in the data. And how do we typically do machine learning? Well, we have some kind of model that is represented here as this kind of brain, and we feed some data into it in order to obtain some prediction, some result. And the data that we feed into this model is typically a series of samples, where each sample is just a bunch of numbers and labels that represents one entity for which we want to predict or classify or perform some task. And these different entities, these different samples, are taken to be independent of each other. Each sample contains all the information needed to classify or predict or whatever. And so each sample is treated independently from the others, typically. And where each sample can be an image, it can be a series of data about an individual. But right now, we also have a lot of data that is not structured in this way. We have a lot of data that is structured in terms of graphs. So in a graph, we don't have independent sample. When we have a graph, we have multiple nodes that are connected to each other by edges. And so the question is, how can we represent this and feed it to a machine learning system? How can we represent that each node is not an independent entity, but it exists in relation with the other nodes? How can we represent that nodes that are connected by edges have some kind of relation to each other? They are not independent from each other. So this can't be expressed in a nice table with one row per node and one column per feature, because these rows are not independent in a graph. So this is where graph representation learning comes into play. Graph representation learning allows us to turn our graph into some tabular data that can then be fed to the machine learning system. And the property of graph representation learning is that these samples, these embeddings, we call them, let's say one per node, that we obtain from the graph, they include information about the relationship between the different elements in the graph, about the relationship between the different nodes, how they are connected, how much they are connected, how far away from each other they are. And so basically, graph representation learning allows us to encode all this information in each row, so that each row can then independently represent, for example, each node of the graph, and allow us to apply machine learning as we would normally do. So here is an example of what a two-dimensional embedding might look like. So each dot is a node of our input graph, and their position in this low-dimensional space of the embedding depends on how each of these nodes is connected to the others. So for example, we could say that in this case, nodes of the same color are nodes that belong to the same group. And we see in the embedding space, they are mostly located close to each other. So we can say that, for example, in this case, our embeddings encode the information of how close together the nodes are. I didn't put the input network used for this. Good that you recognize it's the Karate Club network, but it's it's like the standard example for graph representational learning. So it's a small graph that contains interactions between different people that were related to this karate club. So, okay, I see that some people join now, so maybe now we have hopefully everyone. So for this reason, we can see that graph representational learning is very important to be able to process this graph data in machine learning tasks. But then how do we actually use graph representational learning in our work? So how can we do this magic that transforms our graphs into some data that can be fed to machine learning systems? Well, it turns out that it's not actually that easy. Why? It's not easy because there are many different techniques available to achieve this, to do graph representational learning. And these techniques have very different properties in terms of what kind of graphs they can handle, how they encode this information, what information they can encode in these embeddings. And also we have many different application areas where we want to use graph representational learning. And each area, switch off your microphones when we are not asking questions. Yeah, that was a question by phone. So we have many application areas where we might want to apply graph representational learning. We might be dealing with social graphs, or we might be dealing with communication networks. And in different graphs, we have different kinds of information, and we have different requirements regarding what we want to do with these graphs. So we can't just pick any technique and apply it randomly. So what is the solution to this? The solution is for us to build some kind of taxonomy that allows us to put some order among all these existing techniques and allow them to choose which technique we should use based on what data we have and what task we are trying to do. And so this is what I will try to do very briefly today. It will be give an introduction of what are the main properties of different graph representational learning systems and what questions should we ask ourselves if we want to choose the correct system for our task. So I will ask if there is any question till now, otherwise I will move forward. Also from the audience in the room here.
I have a question.
Yes.
So when you impose structure in your training data, by default, you are kind of introducing some prior knowledge. And does that restrict your parameter space for your neural network?
So you mean the fact that, what do you mean we are using prior knowledge?
I mean, if you did are independent from one another, there is no structural relation between each other. But since you are feeding it in a graph space, you are imposing some structure information between the individual data set.
Yeah, so the idea is that what graph representational learning will do, it will extract some patterns from this structure. So the graph has a structure, and this structure, we can think it comes from some patterns on which the graph is built. Patterns of friendships in a social network, or patterns of communication behavior in communication networks. And so what these embeddings will do is that they will encode in a low-dimensional space these patterns and how relevant each pattern is to understand each node. And so in some sense, then the machine learning system that will be downstream, that will be fed these embeddings, this machine learning system will be able to recognize and exploit these patterns in order to perform its prediction. So yeah, the machine learning system will use this pattern that encode the structure of the network in order to perform the prediction. That's exactly what we want to achieve. We want to allow the system to see these patterns and exploit them.
Okay, so the way I understood it is that the embedding of the structure is going to be task driven?
We will come to this point later.
Okay.
To this point of task driven, we will come later, and then maybe at that point you will understand, or you will have to ask this question again.
Okay, so you are trying to learn the embeddings.
Yes, we will see how we learn the embeddings later.
Okay, thanks.
So then let's move forward and let's see actually what are the main types of tasks that we solve with graph representation learning. So the first type of task, which is probably the most common, is node level tasks. So we compute the node embeddings. We compute, as I introduced before, one vector, one low-dimensional vector for each of the nodes in the graph. And then what we can do is that we can use this to classify the nodes or to predict some property of the nodes. So I don't know, predict the probability of a guy getting some injury while doing sport, knowing what people he does sport with. But then, in addition to this task, there is one additional task which is very graph specific that we can do with node embeddings, which is link prediction. Link prediction means, given the knowledge that we have, how likely it is that a certain edge, a certain connection that we don't see in our graph, like this one, red dotted line, how likely it is that it will appear, this connection, in the future, or how likely it is that it is there, but we just didn't see it. And we can compute this, do this link prediction, by feeding to some system the embeddings of the two nodes that would be at the ends of this edge. So in this way, we can, for example, see how likely it is that these two nodes will have this edge among them at some point in the future. But this is not the only type of representation that we can extract. For example, we can choose to extract not embeddings for the nodes, but embeddings for the edges, in case we want, for example, to predict some property of the edge itself, the strength of the edge, or some other characteristic of it. And we can also do a different thing, which is extract a single embedding that represents our entire graph. So this is useful if we have multiple graphs and we want, for example, to predict whether a graph represents a molecule that is harmful for a human or not. And then we have multiple of these graphs, and we just want one representation that contains or represents the entire graph in some simple way. So these are the main tasks. But then to go back to what Vanges was asking, how do we actually train our embeddings? How do we actually come up with the good embeddings that allow us to solve our tasks? And for this, there are different modes to do this, different ways that the graph representation learning can actually learn the correct embeddings. So one way is to use unsupervised training. We use this when we have a graph and we don't have any additional information. We just know that we have a certain nodes, certain edges. Or we also use it when we want to come up with some embeddings that can be used for multiple different machine learning tasks. So in this scenario, what we do is that we have our graph on the left. Graph representation learning provides us with some embeddings. And what we do is that we want to make sure that our embeddings contain as much information as possible that will help us to reconstruct the graph. So what we want to do is that we want to be able, in some way, to, starting from our, for example, our node embeddings, to be able to predict exactly what edges are in the graph. And in this way, we can basically train the system to produce the embeddings that best approximate our input graph. In this way, the embeddings contain information on the graph and they don't require any additional knowledge in order to be trained. And because they just represent the graph without any additional bias, we can use these kind of embeddings as input to many different types of tasks. If we have multiple models that we want to use, multiple predictions that we want to do, we might be able to do that using this approach. On the other hand, do you have a question? No, okay. Yeah, indeed, it's very similar to some techniques used to natural language processing. And indeed, some techniques for graph representation learning are very strongly inspired by natural language processing. Yeah, in some sense, as you can use this to model the structure of sentences and words in a language, you can model the structure of nodes and edges in your graph. So yeah, it's similar to natural language processing in some sense.
Lodovico, could you please repeat the questions when you answer a question from the class, because we cannot hear them at all, so we only hear the response.
Yeah, okay, sure. In this case, it was not a specific question, it's more like the fact that this looks very similar to natural language processing. And indeed, the answer is yes, it looks very similar because some of the techniques are similar and some inspiration has been taken from natural language processing. So unsupervised training is not the only approach. We can also do some semi-supervised training. And we do this when instead we do have some additional knowledge. So for example, we want to do some node classifications and we know the actual true labels from some of the nodes in our graph. And then we want our embeddings to be specifically trained in order to provide good classification. So in this case, we do the same thing, we encode the graph in our embeddings, but then we feed these embeddings to our classifier, for example. And in this way, we can measure the loss function for those nodes. In this case, we have two nodes for which we know the actual label, so we can apply a loss function there. And based on this loss function, we can find out how good our embeddings are for this task, and we can optimize the embeddings to solve this task in a very accurate way. So these embeddings can probably be better to solve the task, but they will not be able to generalize well to other or to different tasks. So these are fine-tuned embeddings for a specific application. And then we also have supervised training, which is used when we are dealing with graph embeddings, where we want a single representation for a graph. And then for some of the graphs that we do have some labels, or we know the ground truth. And so again, we can backpropagate from our machine learning model to our graph representation learning system. And so we can teach our system to produce the best embeddings for the specific task at hand. So are there any questions on these different ways to train graph representation learning models?
I have a question.
Okay, let's start with Vanjush.
So if you go backward from, so you're trying to construct the graph on the data, you're trying to learn the graph on the data.
Yes.
And if you have an unsupervised learning task, and you have a semi-supervised and a supervised. So in unsupervised learning, you are trying to learn some kind of the backbone of your embedding, and then as you progress further with more supervision, your structure becomes more specialized. So instead of having just a backbone graph, you are also having some additional structure which are task specific.
Yes.
So that was a question. That means it's.
Yeah. So basically, unsupervised only uses the input graph, while semi-supervised and supervised training require you to have some specific downstream task, and you must have some a priori knowledge about this. So you must know some of the labels that you want to predict, or some of the behaviors that you want to predict, in order to be able to teach the graph representation learning system to optimize for that. So you can teach, no, these embeddings are not giving me good results. Please modify the embeddings so that I can get good results for those nodes or for those graphs that I have the correct answer for.
Okay.
In some sense, it's like when you train a normal machine learning system where you have some training examples and you use these training examples to train the weights in the machine learning system until the machine learning system can provide you good answers. And in some sense, you can also do this for the embeddings. So you're also training the embeddings or modifying the embeddings so that they are the best one to answer your specific question.
But when you are training a supervised on a supervised task, do you lose some of the content that you acquired when you did unsupervised training?
Yes, you might lose, or better, the system will focus on those characteristics of the graph that help you answer your question. So while unsupervised learning will focus on those that allow you to reconstruct the graph, here you will focus on those that allow you to answer your question, which means that some things that are useful to reconstruct the graph, but not useful to answer your question, will be discarded. Okay. On the other hand, some things that are not very useful to reconstruct the graph, but are extremely useful to answer your question, might get a more important position in the embeddings that are being trained. So yes, you are prioritizing certain patterns that help you answer your question.
Okay.
Make things clear, you don't have to do supervised always after unsupervised training.
Yeah, so let me come in here. So Ahmed was asking, you don't have to do unsupervised and then supervised. So the thing is, no, I presented them in this order, but these are alternatives. You don't do them one after the other. You either train unsupervised, or you train semi-supervised, or you train supervised. I guess you could pre-train unsupervised and then fine-tune semi-supervised, but typically you don't do that. Most systems, they just choose one of these three techniques depending on the problem statement, and they will use one of these three approaches only.
Yeah, I think they can go for unsupervised training if they want to use that for a general purpose, or if they have a larger scale data graph. So with a lot of nodes or maybe graph, you can have an embedding from unsupervised training, which would serve a general purpose.
So you are asking if a motivation could be the fact that with unsupervised I produce just one representation and I can use it for multiple tasks.
Yes, and for example, if you have a large graph or many graphs, then I would go for unsupervised training all the time. Like that could be one of my motivations for unsupervised training.
Yes, one motivation could be the fact that you have a large graph, as you said, and you don't want to have to run multiple trainings for different specific downstream tasks. However, I do believe that many companies actually look into semi-supervised even for large graphs because of the additional benefits of semi-supervised training. Also because we will see that there are different techniques. If we manage, we will see that there are different techniques, and some of them are most suitable for unsupervised, other for semi-supervised, but some of them are most suitable for certain types of graphs than others. So it's not just a choice of unsupervised or semi-supervised. This is one of the things you have to consider. There are other things that you have to consider when you make your choice. Yes.
But as we discussed previously, you might reconstruct some other graphs, higher order graphs, and then it becomes also maybe not so general purpose specific domains. We say Susanna could provide you with some graph that goes from some motifs from the initial graph, and then suddenly the embeddings will be very different and serving very different purpose.
So
Did we discuss that also? Or?
yeah, so here Sharunas is going a bit forward and asking regarding the fact that we can use unsupervised training, but at the same time we can also add some bias to this unsupervised training in order to reconstruct not the original graph, but some other graph that we are interested in. Now, this is something that is possible, but in my opinion, it does not go against this idea of unsupervised training as general purpose, because you are not introducing a specific task. Your bias might put more emphasis on certain nodes, or on certain features, but its emphasis is not related to a specific downstream task. So you still could apply that to multiple tasks that require that particular emphasis. So in some sense, yes, you could make it less general purpose, but it still would not be task specific, because you are not actually learning on a specific downstream task.
But not role.
Yeah.
If you a little bit massage the outputs graph with motifs, then you can do just role, but it will be completely not in detection.
Yeah. If we have time, we have a slide on that. Yeah. If we have time, we have a slide on that. So. It's okay. So the question is, why is semi-supervised learning considered semi-supervised? So it's semi-supervised in the sense that you only know the actual correct answer for a few of the nodes. However, your system during training sees all the nodes. So your graph representation learning sees not only the nodes that have a label, it also can see the nodes that do not have a label. They are also included in your graph representation learning part. And this is why it's semi-supervised. You only have correct answer for some nodes, but you can see all nodes. This is against the requirement of supervised learning, where the nodes that you train on are those for which you also have the labels, and you do not insert in the training phase those data for which you don't have labels. Here instead, the data for which you don't have labels, which might be your test data, or might include your test data, it's included in the training phase. So you don't have the strong separation of training data and the testing data, or actual production unknown data. So it's all together. And so you can use this extra knowledge to get more precise results. No, I don't have a slide more on this. So the question is, how can this model learn from these few labels? How can it learn to generalize? This is kind of the question,
yeah,
correct?
Like, yeah, it's like you're going to start, for example, unsupervised training, and then you're going to compare the training on these few labels you have, or you're going to do them in like...
So what you do is that you compute these embeddings, and these embeddings, when they are computed, they get information from the nodes around you. So the embedding for a specific node is influenced by the nodes that are around it. And so basically, if the node you are considering has a label, the prediction that you will give for this label will be influenced by the nodes that are around it. So in some sense, and even if you don't know the real labels for the nodes around it, you will still use their embeddings, you will still use their information to construct the embedding and thus to provide the prediction for this specific node, which means that when you then backpropagate, you will backpropagate also to these nodes for which you don't have the labels. So these nodes participate in the training because they still provide you context around your target node, even though you don't know what their labels are. Here, no, here is not about reconstructing the graph. Here is about understanding how the relationship expressed by the graph, these edges, influence the prediction of the nodes.
So I have a question. So for the
No, it's not really okay. From a technical perspective, this is not supervised, because in supervised learning, you would have to exclude all data for which you don't have a label. But we can, yeah, but we can go to this later. Otherwise, we will not finish. Banjush had another question, right?
No, it was me, Deva. So what I was trying to ask is, so for the semi-supervised learning, the labels that you see, the sparse labels that you see, so the whole graph the labels must be a superset, right? I mean, the other graphs which you are going to...
Wait a second. Can you speak a bit louder, because I have a hard time hearing you.
Can you hear me now better?
Yeah, now it's a bit better, yeah.
All right. So the labels in the semi-supervised graph that you have, from which you try to predict the other labels, let's say, these labels are superset of all the unlabeled nodes also, right? So the labels of the unlabeled node must be within the set of this 2L that I see, right?
So this is not mandatory, but of course, it's like when you train a normal machine learning system. If you want to get good results, your training set must represent all your classes in a good amount. Otherwise, your system will not learn those classes that are underrepresented. So yes, those nodes for which you do have the labels, well, you must have some nodes for each label. Otherwise, the system would not be able to understand what are the patterns that are behind each label. So in some sense, the same constraints that apply to standard machine learning also apply here, in the sense that you do need to have good representation of each class.
All right, okay, thanks.
Lodovico, can I ask a question? So could you please give a real world example of a learning, of a case where each learning mode would be suitable? For example, a real world example where we would need to use GRL in an unsupervised learning mode. And of course, for the other learning modes as well, just to make it more practical.
So the question is, again, just the learning mode is not enough to choose. I mean, for a specific application, it's not just the learning mode that will be needed in order to provide good predictions. But for example, for one example that is usually used for unsupervised training is, again, the idea of link prediction, where I want, for example, to predict how likely it is that two people will become, in a social graph, that two people will become friends, just knowing the structure of the graph, which will already give me enough information of how many common friends they are, how closely connected these two persons are in the social graph. And this would probably give me enough information to try to predict what is basically the what is basically the likelihood that there will be this connection between these two people at some point in the future.
Okay,
yeah,
thanks.
I don't have that. But then instead, for semi-supervised, many examples focus on classification tasks, where, for example, you have authors of scientific papers as nodes, and you have collaborations, co-authorship as edges, and you want to predict in which field each author works, and you have some extra information, some extra metadata usually extracted from text that helps you in this. So you have some also additional features, and you try to also use this extra information to aid you in doing this classification. And this is typically a semi-supervised setting where you say, okay, I pick a few authors, and for them I fix that I know the label, and then I know what area they work on, and then I try to predict for the others. Instead, the fully supervised, as I said, is really for graph embedding, where you have multiple separate graphs and you want to predict something about each of them. So if this answered the question, then I think I will.
Yeah, sure.
I will.
I have a last question.
Yeah, go.
So if you try to reconstruct the embeddings from the unsupervised and the embeddings from a supervised into a graph, which graph will be more connected?
Oh, okay, sorry. If you try to reconstruct from unsupervised and reconstruct from semi-supervised.
Yeah, the graph from respective embeddings. Which one do you think is going to be more connected?
Well, I think this really
On
depends
average.
on what. There is no answer for this. It depends on what system you use to build the embeddings and what system you use to actually reconstruct it. So there is no answer for this, but in general, I would say that all these techniques should provide you, if they are implemented correctly, and if they are adequate solution for your specific problem, they should provide you with a graph that is very similar to the original one. So I would say the average degree should be the same as the input graph in all cases. But again, this is very specific to what you are doing, what application you are doing.
I see. And is there any constraint that can give you a closed form solution for the unsupervised learning?
No.
Okay.
For some of them, there might be, but most of them don't have a closed form and you solve iteratively.
Okay, thanks.
Can I have a question? Quick question.
Wait a second.
One sort of way to invent a graph is to take an eigenvector, prominent ones, and try to embed it.
Yeah, you could build. Okay, I'm suggesting that indeed, if you use spectral, if you basically use the eigenvectors of the Laplacian matrix of the graph.
Or of any, I mean, this will be one of the solutions. You can have a graph can be represented in many matrices, and usually eigen decomposition of that matrix by taking specific vectors would give you coordinates in this low-dimensional space that you can probably very often successfully use for your.
Yeah. So yeah, a possible way, yes, is to just basically do eigen decomposition of some matrix that represents the graph, and this would provide you a solution that has a closed form. Then, of course, the point is this closed form is still needs. This still needs to be. You can't compute it in with a closed form because the closed form is still too hard to compute. But most approaches don't have a closed form. Most approaches have only iterative solutions. I think there was another question that was starting.
Yeah, I just wanted to ask about the techniques they use. They use encoder decoder here for doing this.
Some techniques use an encoder decoder architecture. Yes. Many of the oldest techniques are basically this encoder decoder, but indeed, even if most recent papers don't frame it in an encoder decoder setting, you can still think of all these systems as encoder decoder systems, where the encoder is the part that produces the embedding, and the decoder is the part that takes the embeddings and gives you something from it, for example, a reconstruction of the graph. So yes, encoder-decoder architecture is a pretty standard architecture for graph representation learning.
Cool.
And there are, of course, multiple techniques that change what these encoders and decoders will be.
Thanks.
So I will move forward to the next important part, and then we will see for the others. So the next important part is, until now, I only talked, or I almost only talked about nodes and edges, but graphs can include additional information, typically in the forms of features that are attached to the nodes and to the edges. Or we can also have some graphs that are heterogeneous, which means they have different types of nodes and different types of edges. So we can think, for example, of a social graph where we have edges that represent friendships and other edges that represents co-working. So these could be represented as different types of edges, or alternative as edges of the same type, but with some features connecting to them that explain what type of relationship they encode. And here is a graph, very simple graph that instead has some features on each node. So each node has a feature which is its color. Now the question is, if we are feeding this graph to some machine learning system, what is important to get our answer? Is it important just how the nodes are connected to each other, so the topology of the graph, or is it also important, or are these extra features also important? Well, it depends on the kind of application, but there can be many situations where we want to use both. So to do a good prediction for a node, we need to know its features, but also how who its neighbors are and how its neighborhood is structured. How can we put these two things together? Well, the simplest solution is to just take our embeddings, as we discussed before, very simple embeddings, computing based on the neighborhoods, and take the feature and join them together to give them as input to a machine learning system. So, for example, these are our embeddings. Let's consider this node pointed by the red arrow. And to the machine learning system, we will input our embedding vector plus our feature. So we will have one more input to our machine learning system, and the machine learning system will give us some answer based on this. But the problem in this approach is that our embeddings tells us what is the structure of the nodes around our target, and the feature tells us what feature our target has, but we lost information about what features our neighbors had, because we computed our embeddings based on the structure of the graph only. An alternative can be to compute our embeddings by taking also into consideration the features when we are computing them. So we can have some techniques that instead produce embeddings that look like this. So embeddings that not only tells us what structure the neighborhood has, but also what kind of features are present in the neighborhood. So the embedding will be able to tell us, okay, our target blue node has a lot of green friends and a few orange friends, for example. And this can be very important in order to provide an accurate answer regarding the behavior of our target node. So we talked about the need to choose whether we want to do unsupervised, semi-supervised, or supervised. We also need to talk about whether we want to consider features separately from the embeddings, or whether we want to merge them together with the embeddings in order to provide an answer. And what technique we should use will depend on the kind of problem that we have. So this part, it's already a bit late. I will go very briefly through this part. So here I would have explained you the difference between two major families of graph fragmentation learning algorithms, transductive and inductive. But basically what I will just tell you is that in transductive methods, what we do is that we directly calculate one embedding for each node or for each edge of the graph. And we directly optimize these embeddings to solve our task, if we have, otherwise to reconstruct the graph. On the other hand, well, let's just not go through the code, but on the other hand, in the inductive approaches, we will have some function. And what we want to do is that we want to find the best function that can produce these embeddings. So we are not calculating the embeddings themselves. We are training a function that can compute the embeddings for us, starting typically from some features of the nodes. So what is the difference between these two approaches is that the first approach requires you to compute a separate embedding for each node. And if your graph changes, if you get some new nodes that are added, you will have to recompute the new embeddings. On the other hand, if you computed a function that can produce the embeddings for you, then you can just apply this function to the new nodes, and you can in this way get a good approximation of what their embeddings would be. So transductive approaches provide you direct the embeddings and do not generalize very well to nodes they didn't see, while inductive approaches can generalize well to new nodes because they can learn a function that can take some features, some patterns in the features or in the neighborhoods and use them to build the embeddings for you. And typically the choice between transductive and inductive is related to the previous two choices that we've seen. So unsupervised learning without any feature is typically a transductive approach. It's typically done with transductive approach, while inductive approaches have been studied mostly for when there are features available and for when we can train this function based on some semi-supervised labels that we have. But yeah, I will not go too much into the details of this. And I will instead move forward to quickly show you what Sharunas was mentioning before, which was about the fact that in all of this, we didn't talk a lot about how neighbors can affect the representation of a specific node. We just said we use the neighborhood of a node to build its embedding so that the embedding can reflect the situation around this node. But how we do this can greatly affect the results. So let's look, for example, at this graph. So this graph was used as input for a graph representation learning system. And then the embeddings that were produced were used to assign a different colors to different areas of the graph. And as you can see, to different nodes, and as you can see in this picture, nodes that are close to each other have the same label. So what the embeddings produced here are telling us is that they are able to provide us good close communities in the graph. But this might not always be what we want. In other situations, we might want to see some other kind of patterns. And so for the same graph, you can see different embeddings produced using a different approach, give us a completely different coloring, where now, instead of recognizing as similar those nodes that are close to each other, we recognize as similar those nodes that are in similar places compared to others. So for example, we can see here that the yellow nodes are nodes that are mostly at the periphery of the network with only a few connections, except for a guy in the middle that I don't know what's doing there. On the other hand, the red nodes, we can see they mostly form groups that are well connected to each other. So we can see these kind of balls of red nodes with a lot of connection with each other. And we can see the blue nodes that we can see they act as some kind of bridges connecting different groups of nodes. So for example, connecting yellow nodes to red nodes or connecting two separate groups of red nodes. So what I'm trying to say, without going into the details, is that depending on what patterns you want to extract, depending on what problem you want to solve, you want to highlight similarities between different groups of nodes. And this is done typically by manipulating what the concept of neighborhood is. So how much different neighbors of each node affect the node itself. So, well, I will just skip the slides and I will conclude by giving you some examples of actual things that have been done with graph representation learning techniques. So it has been used to predict properties of different molecules. So the nodes in the graph are our atoms, the edges are the bonds between them, the chemical bonds, and we can predict if a molecule is harmful or not to the human, for example. We can, of course, the most common thing is analyzing behavior in social networks, predicting friendships, predicting the spread of news across the social network, for example. But then also some more fancy stuff like reasoning on knowledge graphs, where knowledge graphs are basically these graphs where we connect different concepts to each other with edges that tell us how these concepts are related to each other. And graph annotation learning can be used to represent these graphs and to be able to reason and draw conclusions. Like, for example, if we know that Leonard Nimoy has starred in Star Trek, and that Star Trek is a science fiction series, we can say that Leonard Nimoy has starred in some science fiction TV series. So we can perform reasoning and inference on these graphs using graph representation learning. And then, of course, I was thinking recently, how can we apply this for our project? And there are different potential applications. So, for example, we might be interested in seeing how social interactions affect sport activities. So, for example, how my behavior when I go training at the gym is influenced by the people I interact with at the gym, whether I am motivated by them or whether I am not, and whether I try to mirror them or not in my training. Or from a perspective more from the side of Internet of Sport devices, we can check the network activity of these devices as a graph, and we can try to understand something like, for example, detect the potential malware or identify opportunities for optimizing the communication between these devices by analyzing the graph of their communications. So yeah, basically this was a very, 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 very quick review of what is out there and of what questions one must ask himself when he wants to apply graph representational learning techniques. Now, of course, this field is also very much still a research field, so there are many open questions, like how can we do graph representational learning on graphs that we don't completely see or that change quickly? Or how can we perform these representation tasks without any central view of the graph, but by doing it at each edge device separately? Or even how can we use context information to provide more specific embeddings when we have nodes that are part of many different communities and their behavior within each community can change based on which community the node is interacting with. So whether we can include additional information in this embedding process. So yeah, I hope I made the topic relatively clear and I gave you an introduction of what the field is and made you maybe interested in trying to explore this field to see if it can apply to your research. These are some very basic references that introduce the field with more details and with more links to other papers. And now I will be very happy to take any other questions you have. So I see that Vanjush raised his hand using a feature that I didn't know existed. So
yeah, I found it out like when I was.
Okay. So good to know that there is this feature, and Vanjush will tell us how to use it. But okay, so what is your question?
How do you deal with the memory complexity? You have to truncate the data to fit to batches, and how do you relate batches to one another?
Good point. So memory issues are one of the issues with graph representation learning techniques, especially with some of them that require you to load the embeddings for the entire graph or for a large portion of the graph in memory at the same time. However, there are other techniques that do not require you to load a large amount of information at the same time. So for example, there are some techniques that require you to just load a pair of nodes at each time. And basically, you basically, at each time, just take two nodes that are related to each other, and you optimize the embeddings so that these two nodes are linked together in the reconstructed graph. And then you can forget about them and take another two nodes and repeat this task a pair of nodes at a time. And this allows you basically to not have high memory requirements. You don't need to load all the data at the same time.
You're researching.
Or you also have other, you can also have other techniques that instead perform some kind of sampling of the neighborhood so that only a subset of the nodes is needed for a certain prediction. And I'm getting told that when you start doing these things, this, of course, the fact that you don't need to load all the data is also a good tip on what direction to go to decentralize this. So you don't need to have a full view of the system. You just need to have a small view of who is around whom. But yeah, it's very much dependent on the specific algorithm. But there are many algorithms that do not require to load large amount of embedding at the same time.
Thanks. The only issue that I have with understanding is that you are trying to have a global outlook of your structure by having a local outlook of pairs of data sequentially.
Yes.
Isn't that a bit, I don't know, it doesn't make me feel comfortable to think about it.
It works.
Okay.
I can tell you it works. And yeah. So basically, Sharunas is suggesting good answers to these questions. So he's suggesting, yeah, that you only need, you only look at a local view of who is your neighbor, but then if you iteratively apply this algorithm, your neighbor will have a look at his neighbor. And so in some sense, the information will propagate across all network by doing some hops, one hop at a time in some sense. Excuse me. So the information will eventually propagate to the whole network. So by just looking at your neighbor, you will end up collecting information about the entire area, the entire network, or at least a wide area of the network, depending on the technique.
And what's your underlying assumption that you are having, and then you're learning on top of it? I mean, how do you think of your inductive bias in this case?
Oh, this is a hard question. Underlying assumption might be the fact that we are assuming that the information we are collecting over the network is useful for answering our question. So especially when you do semi-supervised or supervised learning, you might end up with a system where you collect certain information, but then you don't really use it because it's useless for the specific task. So you might end up that you are basically applying graph representation learning where maybe you didn't need even to collect information from the other node, you just needed to check their features, and from their feature you could directly get your answer. So in some sense, you are assuming that whatever features you are collecting, whatever information you are collecting from the network with the specific approach you choose is relevant for the topic, for the answers you want to get.
Okay, I'll think about it, but I have a last question. How do you see this being used for density estimation?
Define density estimation. I have no idea what density estimation means.
Like if I have a lot of data, I want to fit some like Gaussian. I mean, according to the central limit theory, it doesn't matter where are the data from, but if I sample from them, they should go around a Gaussian distribution. If I'm not talking about structure, just like individual data features. Let's say if I have a fashion MNIST and I want to build how are the features distributed, at the very center I will have the average features. That would be like let's say it's going to be like summing up all the values of the fashion MNIST, and they are all going to be centered at the center of the distribution, and all around there are going to be still images, but varying as you go further away from the center.
And what you want to do is to estimate this Gaussian distribution
of individual features without, yes, of individual data, let's say.
But then this is independent from the structure of the graph. So it would be useless to use graph representation learning. You would just collect the features from all the nodes and disregard the actual structure. You would just consider the feature of the nodes and not consider whether the edges exist or not. So in some sense, this is some kind of aggregation that you can do without considering the edges.
I mean, yeah, you can do that without considering the edges, but I'm just asking if it is possible to like make it better or like with this type of representation.
I don't think that graph representation learning would help you with that because, as I said, if your behavior that you are trying to model does not depend on the structure of the graph, then you are not getting any more information than you would get by just applying standard machine learning techniques. So it would not make sense to go through graph representation learning because it would make it more complicated, more time consuming, and probably less accurate. So if the general question is that if you don't need to consider the edges to solve a problem, then you don't need to use graph representation learning to solve that problem. So I would say it's, in this specific case, it's not needed.
Okay.
It won't add anything.
Okay, thank you.
But yeah, okay, important thing, yes. It's really important when you consider to use graph representation learning that you consider what you're trying to achieve and what are the information that are useful for this.
Okay, thank you.
So are there any other questions? Either from Zoom or from the room that I have in front. Yeah, I will go to the part about features. Ah, okay, sorry. Okay, here. So I didn't, so the question is, how does what I explained regarding embedding features, how does this compare to graph neural networks is the question. Now, I didn't introduce the concept of graph neural networks in this presentation. However, this slide is very much inspired by graph neural networks in the sense that graph neural networks are a family of techniques for graph representation learning. So the graph neural networks are a family of techniques for graph representation learning, and they are a family of techniques based on deep learning that they are inductive systems that train this function that produces the embeddings, and they are heavily relying on the features of the nodes as the starting point for this function to compute the embeddings. So yes, when you are dealing with features, with the graphs that have features, graph neural networks are one of the most advanced techniques that you can use to consider at the same time both the features and the topology and produce embeddings that can basically use both these things to produce the output. So graph neural networks are typically inductive systems for semi-supervised learning on graphs that are enriched by features, though you can apply them to other situations as well. But yeah, they are one of the main approaches when you're dealing with features. Yeah, yeah. So yeah, yes, you are correct. So Sharunas was saying about the fact that with graph neural networks, basically they consider both the local features of your nodes and the structure of the network, and they can learn which of these is the most important. So you can, if you're not sure what is important in your network, you can use GNN, and it will find out by itself what is important. The thing is, yes, it's a bit dangerous because you might end up getting very good results with a GNN that you would also have had by not using graph representation learning at all, because the GNN internally uses deep learning. So it could just, it could basically decide internally to disregard the topology. But yeah, before going to Vanjus, who has another question, I will just very quickly, given that we are here, just say that here we have two main families of techniques. On the left, those based on similarity matrix factorization, and on the right, deep learning. The ones on the left are those that are typically transductive. They produce one embedding for each node, while the ones on the right, based on deep learning, they learn a function, which is typically a set of weights in a deep learning model, that can produce the embedding starting from some feature or some information. But then this does not mean that the left-hand side never uses features, because you can use matrix factorization also with features. And on the other hand, you can use these deep learning techniques without features, even though it's not their main setup. So you have to go technique by technique. And the ones that I put in italic on the bottom are some of the main techniques in each category, and can be a good starting point for research in a specific area. I think there was another question. Someone?
Yeah, hi. Can we go to the transductive and inductive slide, please?
Yes, sure.
Yeah, so here when we're doing this algorithm, right, choosing something and then going down to 5, repeating from 2, here when we're doing this, does the dimensionality of the embedding change, or it will remain the same dimension?
You mean how, let's say you're meaning how long each embedding will be?
Yeah.
So typically we would keep it the same. Actually, I'm inclined to say all techniques that I've seen keep it the same, because
okay.
it's the same. As an approach, it's like when you train a deep learning model, you don't change the dimensionality of the weights between iterations. You just change the values until you get the optimal ones. So in a sense, you are training it in this way.
And how do you choose the best dimensions?
Well, that's a big question, a big problem. It's, in general, it's an hyperparameter. So you can do hyperparameter search to find the best one. But yeah, you have to have a good guess at the beginning, because of course it takes time to do a hyperparameter search, especially on large graphs. But yeah, in general, it's a hyperparameter that you have to somehow pick. And of course, the larger this embedding dimension, the more fine-grained information you can encode. But on the other hand, you risk overfitting if you have too specific embeddings.
So there are not like general outlines how to choose this dimension, because in word embeddings, for example, the larger the vocabulary and then the larger the embeddings, the better the architecture will work. So here it's like the larger the graph, or the larger the number of connections, the larger number of edges, for example. I don't know.
No, I would say that there is no relation between the size of the best embeddings and the size of the graph. I would say there is more relation between the size of between the size of the embedding and the complexity of the behavior you are trying to predict.
I see. The complexity of the task, maybe also.
Yeah, the complexity of the task, or at least how many different types of patterns that are in the graph that you need to be aware of in order to solve your task. So if the graph is huge, but there are only a few patterns to learn, maybe a small embedding will be enough.
Cool. Okay, thank you.
Because also I've seen people typically use between 100 and a few hundred embedding dimensions. And I've seen these numbers used on graphs with 2,000 nodes and on graphs with 500 million nodes. So,
okay. Thank you.
Usually humans are more complex. If you represent a node as a human with interaction, that's much more.
yes.
So if you represent some product or whatever, which is pretty simple, then you might need much less dimension.
Yeah, so yes, Sharunas is saying the dimension depends on the complexity of what you are modeling. So for example, the example that he was making is if you are modeling human interactions versus you are modeling products and components or items, maybe human interactions are more complex and human behavior requires more parameters to be modeled effectively. But again, yeah, I would say it's pretty much up to the application to decide.
Great, thank you.
The same principle applies. If you apply word to vec, it doesn't matter how many words you have. If you applying it on English, it usually will take lower to smaller dimension than if you apply on a language with like richer morphology, such as Arabic or Chinese. And if you apply word to vec in a different domain, like scientific article or theories, or Shakespeare, for example, text, usually that's more complicated. So you have to train word to vec with like higher dimension to capture such, to be able to express such complexity. So it's pretty much about the task. It's like the graph about the behavior between the nodes, the interaction between them, and the node itself.
Yeah. So Ahmed is saying, in case you didn't hear that, yeah, it depends on the task, and this is also true in natural language processing, where if you are modeling a language that is simpler, or if you're modeling text in a domain that has a simpler structure, then you will it will be enough to have a smaller embeddings. While if you have a very rich language or a very complex topic, then you will need wider embeddings in order to collect all the information you need. So I think Vanjush has a question.
Yes. So I wanted to ask you how, like, if I have some data, I want to know if graph representation learning is a way to go. How do I start with transductive or inductive approach?
So I would say it depends on whether you have features in your graph or not, and whether you have labels or not. So, okay, we are already on the right slide. So the part with the typically is a good starting point. So if you do not have features and do not have labels, then go with transductive. Transductive is also much simpler to understand, at least most of them. Inductive approaches are generally more complicated to understand, but they provide you this, they map more easily to these two situations when you have features and when you want to do semi-supervised learning.
So you mean it's also easier to incorporate prior knowledge about the data in the inductive case?
Yes, yes. In inductive is easier if you have additional knowledge.
Okay.
I think I've heard some other noises. Was someone wanting to ask a question or add something? Okay, no, maybe it was just background noise. So Ahmed has a question.
Yeah, I thought that this slide is related to the previous slide, or they are just independent.
I don't remember what the previous
Because
slide is.
there was a slide when you were trying to in different ways how to incorporate features in your learning. I said you can just concatenate them, or you can learn the feature in the embedding. This is different, right?
So, okay, so what I've tried to explain in the slides up to this point was different properties of different systems. So I started talking about these learning modes, unsupervised versus semi-supervised. Then I moved to this idea of embedding features or not embedding features. And then I moved to transductive versus inductive. And I would say that these could be, in general, almost orthogonal, but then in practice, they are very much related in that certain learning modes and certain types of features are more easily learned, are more easily inserted in approaches that are either transductive or inductive. So as I said, while you can have transductive approaches that embed features, most transductive approaches do not do that. And so typically, if you have features, you would go for an inductive approach. So in some sense, this is in theory independent from the previous choices, but then in practice, you will find that there is some kind of polarization where if you have features or semi-supervised learning or supervised learning, you typically go with inductive. If you don't consider features or don't consider labels, you typically go with transductive. But this is not set in stone.
For now, if I say for now, features could be more like context. You can do that. You can learn that in your embedding, and you can go for any of the two approaches will apply. If you append the features to your embedding, then that will be more like inductive.
So the question is regarding appending the features to the embedding or inserting the features within the actual embedding. So this is from an historical perspective, we first had those approaches that did not consider features, and they were mainly unsupervised approaches based only on topology information. And the first very simple hack, let's say, to also include the feature information was to simply append them, consider these topological embeddings as additional features of each node to be fed to the machine learning system. However, this has in some way evolved in the literature to specialized systems that can basically combine these two while building the embedding. So instead of concatenating topological information and features and letting a downstream machine learning system mix them in some way, you have the graph representation learning system itself mix the features with the topological information. And the advantage of this approach is that because the embeddings depend on the embeddings of the neighbors and on the features, then transitively, your embedding also depends on the features of your neighbors. So in some sense, it's like if you're not only concatenating your features, but it's as powerful as concatenating also the features of all your neighbors. So it allows you to include more information. On the other hand, what it does is that it scrambles all this information so that you can no longer see the real features, but you can only have a view of the feature that is computed by a machine learning model. So you lose some transparency on how these features are handled. So, but yeah, you can also have transductive approaches that do this. So you can have matrix factorization approaches that try to factorize together the adjacency matrix of the graph or some similarity measure of the graph together with the features of the nodes. So you can have also transductive approaches that do this, not only inductive ones. It's just that inductive approaches are more common for feature-based.
I'm not
Graph neural networks are mainly inductive.
The way you fit the features to the graph, the algorithm, the graph neural network will decide if it's inductive or it becomes inductive in terms of features. How they are fit to your model.
So, okay, the question is about whether the way you input your feature affects the choice transductive, inductive. So the specific graph representation learning method you use is either transductive or inductive. So graph neural networks are inductive, no matter if you use features or not, or how you feed your features. GNNs are always inductive, while matrix factorization is by its nature a transductive approach. Yeah. So are there other questions, guys?
I have a question. Regarding the social interaction in sports activities, do you know what kind of data do you need to conduct this kind of analysis?
So, sorry, I didn't understand well. You are asking what kind of data would be needed to perform this social interaction analysis?
Yes.
For sports?
Yes.
So I don't have the data. I would imagine you would need some data that tells you how people or who do people interact with when they do sport activities. So for example, it could be very simply the log of a gym that tells you that tells you who was in the gym at the same time. And you can consider this as a good approximation of who has interacted with whom inside the gym. So when I went to the gym, who was there? Who did I see that might have influenced me when I was doing my exercises?
Okay.
But then, of course, you also would need to make good use of this. Then you would need some kind of features or labels to use. So what are you trying to predict? So for example, you could say that if I go to the gym when a lot of very healthy pro players are going to the gym, then I'm more likely to take inspiration from them and be willing to do a lot of exercise and also become better. While on the other hand, if I go to the gym with my friends who are as lazy as me, we might end up being in the gym, I don't know, drinking a coffee at the cafeteria of the gym, which is not really training, and not actually doing anything. So I would imagine something on these lines, but of course, this is just what came to my mind. The thing about graph representation learning is that you can find articles with things that you could never have imagined, but someone did. So this is just my idea of how it would work.
Okay, thank you.
So any other question?
I think we have to thank Lodovico.
Thank you very much. Thank you very much, everybody, for listening to me for longer than I expected, as usual. So
I'll add it to the content. We need
so I will just use this occasion very quickly to
the customer might be
a few information. So the next one will be in 3 weeks from now, and I have no idea who will present because I also don't have the Excel in front of me. And even if I had it, I'm pretty sure it was left empty. One thing is, I saw every one of you put a tentative date in that Excel by just consider that we're going every 3 weeks. Unfortunately, it will not really be like that, meaning that, for example, one of those weeks is Easter, and a few of those weeks are in the middle of the summer. So those will be moved. So the dates in the spreadsheet are absolutely not binding, except for those in the short term, which means before Easter. And yeah, I think there is one slot empty and someone who didn't pick. So we will check that. And yeah, just that if you have any issues, any questions, any problems, you can just contact me or write on the Slack channel, and I will let you have the recording of this session and the slides as soon as I manage to find out how. So thank you very much for your attention, and see you in 3 weeks.
Thank you.
Thank you. See you.
Thank you.
Thank you.
Thank you. Bye-bye.
What did they write? It was just a thank you.